Perfect. All right, so yeah, feel free to let everyone in. Yeah,
Here we go.
maybe.
Here, I'm gonna stop it so we can see everybody coming in.
Sure.
No, I guess we'll leave it up. I
Ah,
think that's the best thing to do.
all right, sure. As you wish.
Okay, everybody's coming in. Hello, hello. I have to get it so that everybody can send messages to each other.
Mhm.
Okay. A lot of little buttons to fix here. So we have everything configured correctly. Let's see. Okay. So everybody, you can send messages to everybody so that everybody can see what your messages are and your comments and your questions. Good to see everybody today. This is another live class at Atlantic International University. So here at the university, I'll just say everybody is unique and unrepeatable. And that's the beauty of life, is everybody is an individual. And we can all come together and share our different points of view. So today with us, we have Abdulqader Bin Sahl, who is ready
Yes.
to talk to us about green hydrogen. Go ahead and take it away.
All right. Thank you, Dr. Lambert. That was a wonderful introduction. So this is actually my second time being here, and I'm very fond of the community and the students here at Atlantic International University. And I'm very happy to be back. So today I'll be talking about green hydrogen. So I'm not sure if many of you have heard this term, but as we proceed towards the global decarbonization of our industries, green hydrogen has become a very interesting topic. And I believe, to engineers and even non-engineers, perhaps you've heard about, hydrogen cars, for example, coming in. So I think it's nice to be aware of this topic, which is why I'm very excited to begin. So before I begin, I'll just talk about today's content briefly. So we will start with a quick introduction, followed by the hydrogen sources and demand. Then we will discuss the different hydrogen colors. You may have heard the concept of different colors of hydrogen. Then we will talk about the market projections for green hydrogen and the green hydrogen transportation models. Then we'll talk about electrolysis technologies, which are the main technologies for producing green hydrogen, and then the applications of green hydrogen, and finally the conclusion, which will be followed by a quick Q&A session so we can, refresh our memory. All right, so without further ado, let's begin. All right, so we begin our discussion by exploring one of the simplest yet most crucial elements in the universe. Well, that's hydrogen, the first element in the periodic table. So hydrogen is the lightest and most abundant chemical element that exists. When we look at the stars, much of what we're seeing is actually hydrogen in various states within those stellar atmospheres. It's fundamental to the universe structure and to our existence. So, hydrogen is unique because it's colorless, odorless, tasteless, and it's also non-toxic. However, it's also highly flammable, which makes it both a valuable and a challenging energy source to manage. In its most common form, hydrogen exists as a diatomic molecule, so H2, which means that it consists of two hydrogen atoms bonding together. This is the form of hydrogen we utilize for most applications, from fuel cells to synthesizing other materials. Moreover, hydrogen has the versatile capability of being stored as either a liquid or a solid, but this typically requires it to be combined with other elements to facilitate storage and transportation. Understanding these fundamental properties of hydrogen helps us to appreciate its potential as a key player in our pursuit of sustainable and clean energy sources. So as we move forward, we'll explore how we can harness this incredible element to fuel industries, power vehicles, and much more. All right, so let's now dive into some of the most common methods to produce hydrogen, each with its own set of processes and implications. So first we have steam methane reforming, or SMR for short. This is currently the most prevalent method of producing hydrogen. This process involves reacting methane, which is the primary component of natural gas, so CH4, with steam at high temperatures. This reaction produces hydrogen and carbon dioxide as byproducts. So while steam methane reforming is efficient and well established and have been used a lot over the past 50 years, it's important to note that it does emit CO2, which poses environmental challenges, like global warming. So next, we have to be aware of the amount of CO2 and look for other potential production pathways. So other possibilities to produce hydrogen is partial oxidation. So this method is used for converting heavier hydrocarbons, like those found in crude oil, for example, into hydrogen. In partial oxidation, These hydrocarbons are reacted with a limited amount of oxygen, hence partial oxygenation basically, which is less than needed to completely burn the hydrocarbon. So this results in the production of hydrogen and carbon monoxide. So like steam methane reforming, unfortunately, this process also generates significant CO2 emissions. So lastly, we have the electrolytic methods. These involve splitting the water into hydrogen and oxygen using electricity. If the electricity used comes from renewable sources, this is actually emission-free. So we have a new way of producing hydrogen essentially without any CO2 release. So this electrolysis process is gaining attention as a clean alternative, especially as we push towards reducing our carbon footprint. So the first two methods, as I've said, produce gray hydrogen as there is CO2 being released, while the electrolysis method produces green hydrogen if using electricity produced by renewable energy sources. So don't worry about this. We'll be talking more about the different colors of hydrogen so you can have a better idea of what I mean. All right, so let's turn our attention to the current landscape of hydrogen production sources and how hydrogen is being utilized globally. So as we can see in the slide, the majority of hydrogen today is produced from fossil fuels. Unfortunately, this is the case. Specifically, 98% of hydrogen actually comes from these non-renewable energy sources. So natural gas through steam methane reforming, as I've just mentioned, it accounts for 50% of total hydrogen production. Then we also have coal, which is used for about 30% of hydrogen production, which is especially, for example, in countries like China, where coal is more prevalent. This is still a significant portion, especially in regions with abundant coal reserves, like China, for example. So oil accounts for 18% of hydrogen production. However, in contrast, electrolysis, which is the process of using electricity, as I mentioned, only accounts for 2% of hydrogen production. So of this small segment, only 0.4% can actually be considered green hydrogen produced using renewable energy sources. So we can see that even though this process is clean, it's still very not implemented. So we'll talk about what are the reasons and how we can, kind of circumvent this challenge so we can implement more green hydrogen production in the coming future. So as for the demand, the largest consumer of hydrogen is actually ammonia production industry, using about 55% of all hydrogen produced, primarily for the fertilizers. So around 25% of hydrogen is used in the refining industries, so to treat, basically for the treatment of crude oil into varying petroleum products. So for example, the lubricants that you use in your car and all of these processes actually require hydrogen in the hydrotreating and hydrocracking, for example. So the remaining demand comes from methanol production and the other small sectors in the chemical industry. So this graph highlights a critical challenge. While there is a push towards cleaner green hydrogen, the production from renewable sources is still very limited due to the higher costs compared to the traditional methods that we have, like steam methane reforming. So this underscores the importance of technological advancements and policy support to actually shift the balance towards more sustainable hydrogen production methods. So let's take a look at the color coding that I've been talking about to classify hydrogen based on its production methods and environmental impact. So basically, these colors are used to define or let us know how the hydrogen is actually being produced. So gray hydrogen, this is the first or the most common type of hydrogen currently in the production. So gray hydrogen is produced from fossil fuels, so like natural gas, coal, and so on, through processes like steam methane reforming. Unfortunately, this method releases significant amount of CO2 into the atmosphere, making it less sustainable. Then we have blue hydrogen. So blue hydrogen is also produced from fossil fuels. However, the key difference is that there's the use of carbon capture and storage technologies. So I'm sure you heard about carbon capture, where, for example, we have gray hydrogen production, we produce hydrogen and we release CO2, but we try to capture the CO2 being released. This way, we decrease the total amount being released to the atmosphere. And that CO2 could be either restored underground or used for other purposes. So this makes blue hydrogen actually a more environmentally friendly option compared to green hydrogen. Then we have turquoise hydrogen, which is produced through the pyrolysis of fossil fuels. So pyrolysis is basically the process where the hydrocarbons are broken down at high temperatures in the absence of oxygen, resulting in hydrogen and solid carbon instead of CO2. So this process potentially offers a cleaner alternative to the traditional methods. Then we have yellow hydrogen. So yellow hydrogen is produced using electricity from the grid. So the sustainability of yellow hydrogen depends largely on how the electricity is being generated. So if the grid electricity is produced from renewable sources, then yellow hydrogen is relatively sustainable. However, if the electricity comes from fossil fuels, then it may not be much cleaner than gray or blue hydrogen. Then we have green hydrogen, finally, which is the focal point of today's talk. So Green hydrogen is the most sustainable form of hydrogen. It's produced exclusively through electrolysis of water using electricity generated from renewable energy sources such as wind energy, solar energy, hydroelectric power, geothermal, and so on. So this process does not emit any CO2 and making it truly a clean and a green energy source. So understanding these colors and their implications helps us navigate the complexities of hydrogen production and its role in achieving a sustainable future. So let's talk about the green hydrogen market projection. So as depicted on this map, there are currently 359 large-scale green hydrogen projects announced worldwide. So although it's still not implemented a lot widely, we can see that the projection says that it will be, with a staggering expected investment of approximately 500 billion USD dollars by the year 2030. So this represents a significant commitment from various countries and industries towards developing a sustainable hydrogen economy. So focusing on specific regions, let's look at China, for example. China is leading with 53 announced large-scale projects, reflecting an investment of 180 billion USD. This highlights China's strategic move towards becoming a major player in green hydrogen production and utilization. So let's break down these projects actually by their type. So we have gigascale production, where we have 28 projects that involve renewable hydrogen production facilities capable of generating more than 1 gigawatt. So these are the larger projects. These projects aim to produce hydrogen at a scale significant enough to impact the national energy profiles. Then we have the large-scale industrial use projects. There are 141 projects that utilize hydrogen primarily in refining, ammonia production, methanol synthesis, and a feedstock for steel and other industries. So these sectors are crucial as they're traditionally heavy emitters of CO2. Then for transportation, we have 96 projects focusing on the hydrogen role in powering trains, ships, trucks, cars, and other mobility applications, showcasing hydrogen's versatility as a clean energy carrier. Then we have the integrated hydrogen economy, where 56 projects are designed to create a cross-industry hydrogen economy, integrating different types of end users to maximize efficiency and sustainability. Then, as for the infrastructure projects, we have 38 projects that are dedicated to building the necessary infrastructure for hydrogen distribution, transportation, conversion, and storage. So this project is just not a set of numbers. It actually represents a profound shift in how we think about energy, emphasizing the critical role of green hydrogen in achieving our global sustainability goals. Okay, so as we delve deeper into the potential of green hydrogen, it's essential to understand the barriers that currently hinder its widespread adoption. So let's examine these challenges in the sequence they're presented. All right. So first, we have high cost of technologies and technology maturity. So one of the primary barriers is that the high cost with the technologies needed for producing hydrogen. So these technologies are still reaching technological maturity, which often translates into higher expenses for development and deployment, discouraging the rapid adoption and investment. Next, we have the development of large-scale electrolysis plants. So this is crucial for scaling up green hydrogen production. So these plants are capital intensive and require significant upfront investments, which can be a substantial hurdle in moving from pilot projects to full-scale operations. As of course, investors need to know that these technologies are going to be mature enough to invest in, basically. Then we have the availability of electric grid infrastructures for the renewable energy distribution. So the availability of robust electric grid infrastructures that can accommodate and distribute large volumes of renewable energy is another significant barrier. For green hydrogen to be truly sustainable, it must be produced using renewable energy, necessitating grids that are capable of managing the variability of renewable energy sources. As we know, renewable energy sources are seasonal and they come from different types like solar, wind, and so on. So this is very important. Then we have the storage, transportation, and distribution infrastructures. So the infrastructure for storage, transportation, and distribution of hydrogen poses a major challenge. So the existing infrastructures may not be, appropriate enough to handle hydrogen efficiently, required significant investments in new technologies and systems for the safe and effective hydrogen management, as hydrogen is not easy to deal with. Navigating these barriers require concerted efforts from policymakers, industry leaders, and researchers to foster an environment to grow the green hydrogen economy. So each barrier also represents an opportunity for innovation and progress in making green hydrogen, a cornerstone for our sustainable energy future. And lastly, the lack of regulatory and legislative frameworks. So there's often a lack of comprehensive frameworks to support the development and integration of green hydrogen within the energy sector. So without clear and supportive policies, the path to the adoption and investment becomes complex and uncertain. But for example, here in the EU, there are a lot of new policies now promoting the production of green hydrogen. And this is a good step, as when the companies are being incentivized to or supported to build these new technologies, then of course, in this way, we can actually advance the production for green hydrogen. So it's essential to understand how the hydrogen is moving from the production point to the place of use. So as it's not a very easy process. So green hydrogen is a sustainable fuel option, and optimizing its transportation from the production to the end user itself is very important. So I'll be showing you some transportation or green hydrogen transportation models that can be adopted basically. All right, the first model is the centralized model. In this model, hydrogen production is centralized, meaning it typically occurs at a large facility that also integrates renewable power generation. So this facility might harness wind, solar, or other renewable energy sources to generate the electricity needed for hydrogen production through electrolysis. So the process starts with renewable power generation, which is crucial for producing this green hydrogen. Then this hydrogen is being used directly in the production and storage phase where water is electrolyzed in the electrolysis process, and then it's being distributed to the local users. So these users can be industrial complexes, refueling stations, or like for transportations basically, or power plants, among others. So the opportunities for this model is as follows. First, we have the cost reduction. So centralizing the hydrogen production helps reduce costs associated with the transportation and storage, since hydrogen is produced and utilized in proximity to where it's needed. Then we have the availability of utilities. Basically, by being centralized, this model can leverage existing utility infrastructures, potentially lowering the cost and complexity of operations. So we don't have to, provide utilities if it's in a centralized model, since it will already be using the existing infrastructures. Then the hybridization and scale up. So it promotes the hybridization of utilities and simulates the scale up of electrolyzers due to the consistent and large scale demand. Then we can also have the opportunity of integration of oxygen reuse. So this is actually an often overlooked benefit, which is the production of oxygen as a byproduct of electrolysis. And oxygen is a very important chemical in several chemical industries. So this can be actually reused in these various industrial processes, providing more value to the electrolysis, basically. However, this model still faces a significant challenge, which is the limited availability of areas for renewable energy generation near industrial complexes. So in regions where space or renewable energy sources are scarce, this can hinder the feasibility of a centralized model. Now let us look at the other type of model. So in contrast to the centralized model we discussed earlier, the decentralized model for green hydrogen production offers a different approach that aligns with local production and usage. So first, we have the renewable power generation. After the renewable power generation, this has been sent to basically for the electricity transport in the grids. So the electricity is not transported over long distances, but is actually used to power the electrolysis process in the hydrogen production stage. So this proximity between the power generation and the hydrogen production minimizes the energy loss and also maximizes the efficiency. Finally, the produced hydrogen is supplied to the end users who are also located nearby. So these users, like I've mentioned previously, they could be the industrial facilities, the transport sectors, energy utilities, and so on. So for this model, the opportunities are cost reduction. So by producing and using the hydrogen locally, the transportation and storage costs are significantly reduced. This also allows, like the first model, the hybridization of existing industrial utilities with new hydrogen technologies, enhancing the energy integration and sustainability. We also have increased electrolyzer utilization, keeping the production and consumption close together helps in actually increasing the utilization rate of electrolyzers, making them more cost effective, as this is a very huge issue with the current electrolysis technologies. Then for the green hydrogen electricity transport, it encourages the development of regulations that support the local transport and use of green electricity. Also, it provides an opportunity for grid balancing. So the electrolysis used in this model can act as a grid balancer by adjusting their hydrogen production rate based on the availability of renewable energy, thereby supporting the grid stability. However, there are still some challenges for this model. First is that there could be inadequate electricity grid, basically, which means that the local electricity grids may not be robust enough to handle the additional load or variability of the renewable energy sources. So this actually requires upgrades or new infrastructure. The cost of and consequently, this cost of infrastructure can be costly and complex. So understanding this decentralized approach is also important as it represents a scalable and potentially more sustainable method of integrating green hydrogen into our energy systems, particularly in regions where we have abundant local renewable energy sources. Then we have the second model, which is the decentralized model 2. This is actually similar to the first one, where the main difference is that the renewable energy produced is used directly to produce hydrogen and not being sent to the electricity grid like the previous one. And after that, the hydrogen is transported to the end users. So this model actually leverages the existing gas networks wherever possible and potentially integrates new infrastructure developments. So the opportunities are mostly the same. However, for the barriers is that since we're trying to use gas infrastructures or the gas pipelines, these pipelines may not be significant or may not be appropriate to handle hydrogen. So sometimes there needs to be modifications done. And this, of course, is going to be resulting in more costs. So these are just models to keep in mind on how we can actually produce the green hydrogen and actually send it to the end users. All right, so now let's talk about the important part, which is the electrolysis. So electrolysis is the technology to produce the green hydrogen. So before we do that, let us just
Abdulqader, there's a quick
Yes.
question. In chat,
Please.
someone, Aswa says, hydrogen is air, but what is the source of H2 production? From air, or is it breaking water molecules?
Okay, exactly. So in steam methane reforming, we basically use steam, which is water, and we put it through like a furnace where it's breaking, it's broken down to hydrogen essentially. So yes, to answer your question, we use water and we break it down to hydrogen. Yeah, I hope that answers the question.
Yes, I think that does.
Perfect. All right. Feel free to stop me anytime. Okay. All right. So before we talk about electrolysis, let us first understand what this technology is all about. So what is electrolysis? Well, electrolysis is a simple yet powerful process that uses electricity to split water into two basic elements, so hydrogen and oxygen. So even electrolysis, we use water and we split it to hydrogen and oxygen, similar to steam methane reforming, where we also use water as the main raw material, basically. So this process is pivotal in the production of hydrogen, basically green hydrogen. So how does it work? Well, imagine putting two metal sticks, which are known as electrodes, in water and connecting them to a battery. So when you turn on the electricity, actually bubbles start forming around these sticks. So these bubbles are actually green hydrogen and oxygen, basically the green hydrogen and the oxygen gas is being released. So why is it important for green hydrogen? Well, because the hydrogen produced through electrolysis can be used as a clean fuel, because this process actually generates energy without polluting the air, meaning we have no CO2 emissions, unlike the traditional methods like the steam methane reforming. So this slide actually provides a clear comparison of the CO2 emissions associated with the different sources of electricity used for electrolysis. So if we use renewable energy to power the electrolysis process, then we have zero CO2 emissions. So this is depicted by the green line as shown in this slide. However, if we use electricity coming from the grid, then we can see that 18.7 kg of CO2 emissions per kg of hydrogen produced, as shown by the orange line. So although electrolysis can be a clean process, it all depends on where the electricity is coming from. If my electricity is coming from renewable energy sources, then of course I'm going to have no CO2 emissions. However, if that electricity is coming from the normal electric grid, this electric grid might use other type of fossil fuels to produce electricity, and thus there will be some CO2 emissions to take note of. However, comparing it to steam methane reforming, it's around 7 to 9 kg of CO2 per kg of hydrogen produced, which is less than the potential emissions from some grid electricity, but it's significantly more than green hydrogen produced from renewable energy sources. All right. So as we delve deeper
Okay,
into the
I
role
have
of
another question that
yeah,
came in.
sure, yeah.
Green hydrogen relies on renewable energy sources like solar and wind for electrolysis. But considering the variability of these sources, what should be the alternative source? And not and keeping in mind that we want a carbon zero emission.
Okay. So renewable energy sources, there are a lot. So we have, for example, solar, wind, hydropower, geothermal, nuclear as well could be considered. So my question, my answer would be if we have a lot of variability, for example, we try to use more than one renewable energy source to produce the electricity. Because, for example, solar sometimes if it's not the right season for solar, for example, then we can try to use wind energy and a combination of wind energy, hydropower, geothermal, and so on. So my ideal case would be that we have a lot of renewable energy sources which are connected to the grid, and depending on the season, each renewable energy sources will be providing the electricity, or could be stored where it could be later provided. So the answer to that would be to use different as much as possible. I mean, of course, this is complex because every country or every region might have some source more than the other, but try to use as much sources to power the electricity, because otherwise, other than the renewable energy sources, you cannot have zero CO2 emissions. You know, there will be some CO2 emissions. You know, even if you use like, for example, if you use sources like biomass, this also could be a potential use. However, the production and the process of utilization biomass, if you look at the product life cycle, there will be CO2 emissions eventually. So the only clean way would be, of course, to adopt renewable energy sources. Yeah.
All right, thank you.
Perfect. All right. Okay, so let us talk about the current technologies for electrolysis to produce green hydrogen. So each technology has specific characteristics, and currently in the market, we actually have four. So we have alkaline water electrolysis, which is the oldest one and the most viable or the most mature one. Then we have the proton exchange membrane. Then we have the solid oxide electrolysis cell, so SOEC. And finally, we have the anion exchange membrane, which is actually a very current or very new technology for electrolysis. So this table actually provides a comparison to the different, to the different technologies. We can see that the first one is actually commercial with a technology ready level of 9. So this TRL is basically a value, to those who might have not heard about it, is basically a value to let you know how mature a technology is. So 9 means that it's the commercial, and 1 means that it's still very new and it's a research phase. So we can see that the TRL level for AWE is actually 9, which means it's commercial. Then for the proton exchange membrane is almost commercial, so it's early commercial, around 8 to 9. Then for the solid oxide electrolysis cell, it's 5 to 6, so this is the pilot phase. And then the anion exchange membrane is also in the pilot phase, but it's slightly less developed compared to the solid oxide electrolysis. As for the feed, we can see that water is used for all of them, even the solid oxide electrolysis, but in this technology, steam is used instead of water due to the high temperatures, and also CO2 is used as a feed. As for the product, all of them produce hydrogen and oxygen, whereas solid oxide electrolysis cell produce hydrogen, carbon monoxide, and also syngas. If we look at the market share, we can see that actually the current market is completely dominated by alkaline water electrolysis, as is the commercial technology, and a slight portion of the market is actually using protein exchange membrane. But don't worry, we'll be talking more about each technology on its own right now. So let's move on and see each technology. All right. So before I talk about each technology, I'll just like to show you some of the companies. Maybe you have seen some of these companies here, and these are the top players actually in the electrolysis technology. So for alkaline water electrolysis, companies like Nel, McPhy, High Gear, and ITM Power are prominent in this field. So this technology is a mature one, and these companies are well established, having significantly contributed to its development and commercialization. As for the proton exchange membrane, we have Elogen, ITM Power, and H-Tech Systems, which are the main key innovators and market leaders. Then for the PM technology, we know that it's a new and upcoming commercial technology right now, and it's beginning more traction as we proceed. Then we have solid oxide electrolysis cells. So companies like Sunfire, Mitsubishi Power, and Series are actually pioneering this technology. So this is valuable as its ability to operate at high temperatures and integrate with other processes like syngas production, unlike the other hydrogen production technologies. Then lastly, we have the anion exchange membrane. So this is actually an emerging technology working in developing AM technology, which is, it's known for its potential cost advantages and flexibility in operation compared to the other ones. So let us actually talk about each one right now. So let's talk about the most mature or the oldest technology, which is the AWE, so the alkaline water electrolysis. So this involves using electricity to split water and hydrogen in an alkaline environment. So typically using a solution of potassium hydroxide, so KOH, or sodium hydroxide, NaOH, as the electrolyte. So this process occurs in a setup that includes two electrodes, an anode and a cathode, separated by a diaphragm to prevent the gases from mixing. So imagine placing two metal plates in water that contains a dissolved electrolyte, so like potassium hydroxide. When we apply the electric current to these plates at the cathode, which is the negative electrode, water molecules gain the electrons, which reduces them to hydrogen gas and hydroxide ions. At the anode, which is the positive electrode, water molecules lose the electrons, which oxidizes them to produce oxygen gas and hydrogen ions. So the overall reaction results in the production of hydrogen and oxygen gases. So the diaphragm between the electrodes allows the ions to pass through, but keeps the gases separate, ensuring that we have efficient collection of hydrogen and oxygen separately. As for the technology details, the operating pressure and temperature, so it usually operates around 1 to 10 bar. So that's around 1 to 10 bar, and the temperatures are around 60 to 90 degrees Celsius, which are relatively moderate conditions that help maintain the stability and safety. As for the electrolyte, the use of 25 to 30% solution of potassium or sodium hydroxide that increases the conductivity of water, facilitating the electrolysis process. As for the capacity and energy consumption, this can vary widely in size, with some capable of producing of up to 20 megawatts of hydrogen. The energy consumption ranges from 4.2 to 4.8 kilowatts per cubic meter of hydrogen produced. So this makes it actually an energy intensive process. So here we have two images for electrolyzers that use alkaline water electrolysis. So on the left, we can see the cylindrical unit that houses the electrolytes and the electrolyte solution where the water splitting process occurs. The exterior is equipped with multiple ports and connectors for water input, hydrogen and oxygen output, and also the electric connections. So its robust tube-like structure is typical for the industrial electrolyzers because they are designed to handle actually the high pressures and the continuous operation. So the image on the right shows the large-scale setup involving multiple connected units. So this depends on how big or large the system is. So we can see that there are a lot of pipes being connected to this system. Here we have a more a wider system that shows also all the components of the alkaline water electrolysis. So this is a very intricate system actually. So in the middle of the system, we see the KOH electrolysis stack where the electrolysis reaction occurs. Then we have surrounding the stack are various critical components. So the gas separators for extracting and purifying the gases, a control cabinet for system management, which is typical, and then a DC power supply to energize the process. So additional features like the cooling systems and rectifier cabinets ensure the system operates efficiently and safely. So this visualization helps us understand what are the actual components in this AWE system. All right, now let's move on to the next technology, which is the proton exchange membrane, or PM in short. So this utilizes a solid polymer electrolyte and operates under conditions that allow for high hydrogen production purity. The technology stands out for its ability to operate at a relatively low temperature and also by high pressures. So how does it work? Well, imagine you have a sandwich where water is introduced on one end, and in the middle of the sandwich, there's a special membrane. So on the either side, there are the electrodes and the electrodes of the anode and the cathode, where electricity is applied. So at the anode, water molecules are split into oxygen, protons, which are hydrogen ions, and electrons. The protons move through the proton exchange membrane to the cathode, where they meet up with the electrons from the electric circuit, forming the hydrogen gas. So this process results in the hydrogen gas, which is later separated as usual. Then, as for the operating temperature and pressure, so as I mentioned, it's relatively low temperature, where around 50 to 80 degrees Celsius, and operating pressure is around 0 to 60 bar, where the maximum pressure is typically about 80 bar. For the energy consumption, it consumes about 3.8 to 5 kilowatt hour per cubic meter of hydrogen, highlighting its relatively high energy efficiency. As for the capacity, so this technology is actually scalable with units capable of producing up to 20 megawatts, like the alkaline water electrolysis technology, and its footprint is around 700 to 800 square meters. So currently, PEM is at the early commercial stage, and it's already past its initial development stages. So we are expected to see more actual implementation of this technology in the coming years. So this slide provides a detailed view of not the alkaline water electrolysis, this is a typo, of the proton exchange membrane system. So we can see that there's the main electrolysis stack on the left, where water is split into hydrogen and oxygen through electrolyte energy. So to the right, we see the system's integral parts, which are the gas liquid separators that separate the produced gases from the electrolyte, and the H2 purification and dehydration units, which ensure that the hydrogen is pure, the hydrogen is pure and dry for use, basically. Additionally, there's a section for electrolyte storage, which holds basically the electrolyte for this process. All right. Now let's talk about the solid oxide electrolysis cell. So SOEC is a type of electrolysis that operates at very high temperatures, in contrast to the other technologies, between 600 and 1000 degrees Celsius. So this technology uses a solid ceramic material as the electrolyte. The material conducts oxygen ions from the water, or basically steam, since it's at high temperatures. So in simple terms, think of the SOEC as a setup where water vapor is introduced at one side under high temperatures. This split then is split into oxygen and hydrogen. At the cathode, water reacts and forms hydrogen gas and oxygen ions. These oxygen ions then travel through the solid oxide electrolyte to the anode, where they release electrons to form the oxygen gas. So this process efficiently separates the oxygen and hydrogen, providing pure hydrogen gas at lower voltages, other than the electrolytic methods. For the operating pressure, it's at 1 bar, so very low pressure, but the temperature is actually high. But this temperature is important as it improves or increases the efficiency of the process. For the feed, it not only uses water, but also carbon dioxide, allowing it not only to produce hydrogen, but also syngas, which is basically a mixture of hydrogen and carbon monoxide. And this is actually a very important precursor to all the organic chemical industry. Like, for example, methanol is produced from syngas. So currently, it's still in the development stage, indicating that it's not yet fully commercial. So it still requires active research and refinement. As for energy consumption, it's around 3.1 to 3.7 kilowatts per cubic meter of hydrogen produced, which is actually in the lower end for electrolysis technologies, highlighting its potential to be actually very energy efficient. Also, one key important thing about this one is that it uses CO2 actually as a feed. And we know that we're trying to get rid as much as possible of our CO2 in the atmosphere. So this actually could be a technology where we can capture the CO2 and actually use it to produce green electricity. So it's kind of, we're trying to basically minimize waste and produce more renewable energy. Yeah, so let's move on to the last technology, which is the anion exchange membrane. So this is the newest technology. So how does this work? Where it actually uses a special membrane that allows the negatively charged ions to pass through while preventing gases like hydrogen and oxygen from mixing. So similarly, water is reduced at the anode side from the electrolysis cell, and then when the electric current is applied, water at the anode is oxidized to produce oxygen and positively charged hydrogen ions, which are protons. Then, instead of protons moving through the membrane, the hydroxide ions move from the water at the cathode side to the anode to balance the charge, effectively transporting the negative charge across the membrane. At the cathode, the hydrogen gas is produced from the incoming protons, combining with electrons from the electric circuit. So this setup allows for an efficient separation of hydrogen and oxygen with a simple and low-cost membrane compared to the other electrolysis technologies. So this operates at 1 to 5 bar, and actually the lowest temperature of all the other technologies to 20 to 60 degrees Celsius. And this can reduce the energy required and simplify the system design. However, in terms of maturity and capacity, this technology is still in the development phase, and it's currently being piloted with a stack module capacity of less than 0.5 megawatt. So the primary feed is water, and the products are hydrogen and oxygen, similar to the other electrolysis technologies. The lower operating temperature and potential cost benefit make this technology actually appealing for integration into the renewable energy systems, where cost and operation flexibility are critical. However, its development is still in process, and yeah, I'm actually quite excited to see this technology in the coming years. So enough talking about the technology, let's talk about the green hydrogen application. So we have an overview of the green hydrogen applications. So first of all, energy storage. So green hydrogen can be stored and converted back to electricity, providing a solution for balancing energy supply and demand. So where renewable energy sources are, still viable. As for the transport, it also serves as a clean support or a clean fuel option for vehicles, from cars to buses and even planes, significantly reducing the greenhouse gas emissions in the transport sector. It's also a stationary power source where it can generate electricity in stationary fuel cells, offering a reliable and clean power supply for residential, commercial, or industrial use. This also can be used for industrial energy, where hydrogen can be utilized in industrial processes where high-grade heat is actually required. It can also be used for building heat, where green hydrogen can be used for heating buildings through a fuel cell technology or hydrogen boilers, providing an alternative to fossil fuels. It can be also used as an industrial feedstock, where it's a key component in various industrial chemical processes, including the production of chemicals and refining of metals. Then it can be used for decarbonization and synthesis, where it acts as a feedstock for decarbonizing existing industrial complexes, and is pivotal in the production of e-fuels and chemicals, particularly in processes where carbon dioxide is reused. So this enhances the sustainability and reducing the environmental impact. So the versatility of green hydrogen in supporting a diverse application underscores its actually critical role in achieving decarbonization goals across multiple sectors. By integrating green hydrogen solutions, we can actually reduce the dependence on fossil fuels, decrease the carbon emissions, and foster a sustainable energy transition that aligns with the global climate targets. So here is just a quick summary of the different sectors where hydrogen can be used. So the green hydrogen can be used in the ammonia and urea in the agriculture sector. It can be used for refineries, for methanol production, steel factories, or it could be used for direct injection in the gas grid for mobility and e-fuels. So this brings me to the conclusion of today's sharing. So for a sustainable energy future, green hydrogen is the answer, as it represents a key component in achieving a low-carbon future, offering sustainable solutions across various sectors, including transport, energy, and industry. Continuous innovations in electrolysis and other production methods are actually enhancing the efficiency and viability of green hydrogen as a renewable energy source. The growing global investment in green hydrogen technology is driving economic growth. So this actually creates jobs and fosters new industries based on sustainable practices. Lastly, we'd like to the policy and the global cooperation, where supportive policies and international cooperation are essential to scale up the production and utilization of green hydrogen. So in order for us to see more green hydrogen projects, we need to have more policies that support and promote the use of green hydrogen. So we have challenges and opportunities that we saw. Like, while there's still challenges and costs, like the infrastructure and the technologies, the long-term benefits of integrating green hydrogen energy systems will be worth it.